Okay, let's continue. Well, if we look to this expression, which we wrote in the previous hour, we may see that the only variable that changes with time is a phase of the wave, or in other words, we can say that wave travels at a certain velocity, uh, at a certain velocity. So, in order to find the travel velocity of the wave, let's look to this figure and take the fixed point P, fixed point on the wave, and for this point, uh, for this point, phase of the field is okay. For this fixed point, phase of the field is omega t minus kz plus phi is constant, and from from this expression we may find that z is equal to omega t over k plus phi over k minus constant, and the okay, let me decrease a bit more. So the coordinate of this point along z changes in this way, and the velocity, if we know the coordinate of the point which is changing in time, velocity will be the derivative of that coordinate dz with respect to time. Or if we derive this expression with respect to time, we will get the velocity of the point. And okay, if we do the derivation with respect to time, this term is constant. The derivative of constant with respect to time is 0. This term is also constant with respect to time. That's why the derivative of this term is also 0. We have only this term which changes with time, and the derivative of this term with respect to time will be omega over k. And from at the beginning At the beginning, we denoted omega as, no, sorry, not omega, but k we denoted as omega multiplied by square root of mu epsilon. Yep. And from this, we may write that speed of propagation of the wave in the medium is equal omega omega simplifies 1 over square root of mu epsilon. So this is the speed of propagation of the wave in a medium. In the case of empty space or free space, so in the case of free space, Vp will be equal to 1 over mu 0 epsilon 0, which is equal to the speed of light c. This is for free space. In general, speed of propagation is equal to this. Speed of propagation of the wave in the medium. Okay, this is also can be called as phase velocity of the wave, or okay, that does not matter. So okay, we defined for free space, which is c. Okay, so the phase velocity of electromagnetic waves in free space equal to the speed of light in free space. Okay, and uh, this assumption, or not assumption, this conclusion, which says that phase speed or speed of propagation of electromagnetic waves in free space equals to the speed of light c. This assumption should have been suspected. It means you should have suspect this assumption, because as we know, the light is also light is also the electromagnetic wave. Okay, since uh, one one little note, since in materials mu r and epsilon r, in most materials mu r and epsilon are greater than 0. So in these materials, phase speed is lower than speed of light. Okay, uh, this is not so important. So as as the wave propagates, the distance between two successive crests. So look look here. Distance between two successive crests, or distance between two successive maximums of the wave depends both on frequency of the wave and its phase velocity. And we define this distance as wavelength. So lambda can be written as Vp over the frequency, and frequency is equal to omega over 2p. So if we write omega 2p Vp, and yes, I'm also recording the lecture. Okay, 2p Vp over omega, so in turn, which is in turn Vp. So so Vp we said is equal to 1 over mu epsilon, 1 over square root of mu epsilon, and we have 2p over omega square root of mu epsilon, and omega multiplied square root of mu epsilon is equal to k. That's why we have 2p over k, and the wavelength is measured in meters because it is distance. Okay. So in the electromagnetic case, in the electromagnetic case, wavelength lambda can be very short or can be very long. It doesn't matter, and so can be very short. It is, for example, light, X-rays, or infrared radiation also has very short wavelengths, and also electromagnetic wavelengths of electromagnetic waves can be also very long. So these are radio waves, or etc. And okay, for example, if we have a frequency of if we have frequency of 50 hertz, frequency of electromagnetic waves, 50 hertz, what is the wavelength? Wavelength uh, in case of so let's write free free space and electromagnetic wave. Wavelength will be just, we said, Vp over frequency. In our case, Vp is C over frequency. C is 3 multiplied 10 to the 8. Yes, divided by 50 hertz. Yes, Vp over F. And we have the answer, okay, 300 divided by 5 is 60, or okay, here we have 6 multiplied 10 to the 7. No, 10 to the 6 meters, or 6,000 kilometers. Well, if you have a wave of electromagnetic wave of 50 hertz, its wavelength is 6,000 kilometers, or a wave at a frequency of 30, let's say, gigahertz. The wavelength will be C over F. C is 3 10 to 8 divided by 30 10 to 9, and you have 0.01 meter, or 10 millimeters of wavelength. Okay, and from the definition of wavelength, we may define K, which is equal to 2p over lambda. The unit of measurement is radians per meter, and K is called as the wave number. So wave so let's see one example. The propagation of electromagnetic waves in water. So let's read. An electromagnetic wave propagates downward from an aircraft into water. The wave is at frequency of 10 gigahertz. So frequency is 10 multiplied 10 to the 9, or 10 to the 10 hertz. Assume that at this frequency, distilled water has a relative permittivity of 24, and neglect any effect of the interface between air and water may have. So relative permittivity is permittivity mu r. So relative permittivity epsilon r we are given as 24. Okay, and neglect an effect in the interface between air and water may have. Okay, first A, calculate phase velocity, wavelength, and wave number in air. Okay, A. In air, the V phase velocity in air, VPA. In air, we have mu 0 epsilon 0, which is equal to, we already know, which is equal to C, or, okay, or better, let me write the numeric values as well. So mu 0 is equal to 4 pi 10 to the minus 7, and epsilon 0 is equal to 8.854 10 to the minus 12. And the phase velocity in the air will be equal to, so will be equal to 2.988 10 to the 8 meters per second. Okay, the next is wavelengths. What is the wavelength? Okay, wavelengths, we said lambda is equal to phase velocity divided by frequency. In our case, lambda A, which is in air, phase velocity in air divided by F. So phase velocity in air 2.9. So 2.988 10 to the 8 over frequency, in our case 10 to the 10, and wavelength is equal to 10 to minus 2. It is equal to 0.1203, 0.03, or no, better, let me write more precise in millimeters. No, it's okay, 0.03, and is equal to 30 millimeters, 0.03 meters, and is equal to 30 millimeters. And wave number in air. Okay, so let me scale down a bit and continue in the same page. Okay. Okay. Okay, wave number in the air k. We said that wave number is 2p over lambda. Okay. Wave number in the air ka is equal to 2p over lambda a. So 2 multiplied 3, 14 over lambda. In our case, let's write in meters, 0.03. And a wave number is approximately 209.44 radians per meter. Okay, now the next part of the problem, the part B. Calculate phase velocity, wavelength, and wave number in water. Now we are switching to water, where the relative permittivity of the water is 24 and the relative permeability is not given. That's why we take it as 1. From here we know that permittivity of water is 24 epsilon 0 and permeability of the water is mu 0. Now let's compute the Vp of water, which is 1 over mu epsilon and is equal to 1 over 24 mu 0 epsilon 0, or in other words, it is equal to 1 over square root of 24 multiplied 1 over square root of mu 0 epsilon 0. So this is equal to C, and we have C over square root of 24. So phase velocity of the in the water is equal 6 point will be equal to 6.12 10 to the 7 meter per second. And what is the wavelength? Wavelength in the water is velocity in the water divided by frequency, and is equal to 6, 12, 10 to 7 over 10 to the 10, and will be equal to 0.00612 meters or 6.12 millimeters. And the wave number in the water is wave number in the water is 2p over lambda of water, or wavelength of water. Okay, 2p over 0.00612 is approximately equal to 1026 radians per meter. Okay, the final part of the question. Write the electric field intensities in air and water. Assume the electric field and magnetic fields are parallel to the surface of the water, with known but different amplitudes in air and water. Okay, how do we write, how do we proceed with the last question? Let me copy the last question in our new page. Okay. Write the electric field and electric field intensities in air and water. Assume that electric and magnetic fields are parallel to the surface of water with known but different amplitudes in air and water. Okay, the amplitudes of electric and magnetic fields are known, and they are electric and magnetic fields are parallel to the surface of water. Now, let's use the equation which we wrote for electric field, or in other words, the general solution which we wrote. So, okay, here. Yes, of this equation. Let's copy this, two of these equations. Okay. We put them here. Okay. These equations could be helpful for us in order to solve the final part of our problem. Okay, perfect. Now it's perfect. Okay, how do we proceed? We using these two equations, we can write the electric fields in water and air. Okay, we assume that the normal direction is z, and the electric field intensity is on the x or y direction. So the fields in the air are, so electric field in the air R. We said that amplitude we said is known. So let's write E, for example, EA, which is amplitude, multiplied to the E to the power of minus J Ka Z, or in our case EA E to the power of minus J, the wave constant of air was 209.44 209.44 Z. Or if we write it in time harmonic form, air Z and T, we will get the amplitude, which is EA, multiplied by, look here, multiplied by cosine omega t. In our case, omega is 2pf, or 2p multiplied f is 10 to the power 10 t, minus, so k multiplied by z. K is 209.44 z, and phase, okay, initial phase we may assume as 0. And similarly, the electric field in the water can be written as E water. Sorry, let me write water. EW multiplied E to the power of minus J, and K for the water was 1026 Z. Okay, and if we write in time harmonic form, E water Z and T will be equal to E water, electric field in the water, multiplied by cosine. So 2pf doesn't change. 2p 10 to the power of 10 so t minus kz. K is in our case 1026 z. Okay, that's it.